All right, we got one last major topic, by the way, to cover here in Chapter 8, but it is quite short. It's just a brief look at what is called power. First exam of the second semester, as you know, is on Wednesday of this week. Now, on Friday of this week is the last web assignment for Chapter 8 to its normal time, but I do encourage you to work on it between now and the exam as part of your exam preparation. Okay, let's go ahead and get to our last topic here, which is on power. Light, work, and energy. Power is another word that we kind of use in everyday language, but it does have a precise definition. It's defined just qualitatively in the following way. It's the rate at which work is done. But when work is done, energy is used. So you can also equivalently think of it as the rate at which energy is used. Okay, now it's defined actually mathematically two different ways. It's defined as an average quantity first, and then an instantaneous quantity. And by the way, the key word here is rate when describing this quantity power. Whenever you have a rate, you're always talking about something divided by what?
Time.
Divided by time. So it's basically work over time. That's the easiest way of thinking of it. But it is divided up kind of into two parts. There's an average quantity first, average power. Average power, called P bar, and it's equal to work done by a force divided by time. Now it is a new quantity for us, so let's check the units. First of all, in metric SI units, we have work in terms of joules being divided by time in seconds. So we have joules per second. Joules per second is given its own name. Everybody here has heard of it. It's what's referred to as a watt. So for example, let's say that we're operating, as we say, a 100-watt light bulb. What that means is that it requires 100 joules of energy per second in order to remain lit. That is what is meant by a watt. Now, before we go any further, let me clear up perhaps a little bit of confusion you may have, particularly for those of you that are enrolled in AP Environmental Science. You may have heard of something called a kilowatt hour, abbreviated as kWh. Now, a kilowatt hour is not a unit of power, it's a unit of energy. And here's the way in which it works. Okay, first of all, the prefix kilo means 1,000. So this is 1,000 watt hours, like so. And then, as I just mentioned a few moments ago, a watt is joules per second. But then what we're doing is we're multiplying it here by an hour. An hour has 60 times 60, or 3,600 seconds associated with it, like so. Notice that the seconds cancels out, and you're left with joules, which is, of course, the unit of energy. But it's a pretty big amount, notice. It's 3,600 times 1,000. That's 3.6 million. 3.6 times 10 to the 6 joules. Kilowatt hours is primarily used to describe, by the way, electrical energy consumption. Like, for example, if you ever take a look at your family's electric bill, how many of you have ever looked at your family's electric bill? A couple of you have. Believe me, you'll start looking at it when you start paying for it. But you're never going to see the unit written out in terms of joules, because it would be gigantic. Instead, we use this much larger unit to describe electrical energy consumption, a kilowatt hour, which is 3.6 million joules. Okay, now getting back to power, still with the units here, in metric SI units, once again, we have watts. In English units, we use an old archaic term that is now defined and quantified today in a very specific way, usually in the context of, say, the internal combustion engine. And that's what's referred to as a horsepower. I'll give you an idea as to what a horsepower is in a simple problem in just a few minutes, but it's defined, first of all, in the following way. Okay, first of all, in English units, we didn't do any problems associated with it in calculating work, but work as force times distance is pounds times feet in English units, a foot-pound. And then we're dividing it by time in seconds. So in English units here, the units of power are just foot-pounds per second. We specifically define now what is meant by a horsepower. Is that the door? We specifically now define what is meant by a horsepower, 1 HP. It's 550 foot-pounds per second. You don't have to memorize this or know it off the top of your heads or anything like that. It's also equal to, in metric units, 746 watts. Okay, the term horsepower is an old archaic term that goes all the way back to pre-industrial times. It was just kind of a loose description of how much work can be done in the course of an hour by some sort of beast of burden, a horse and whatnot, in an agricultural sense. We have now since defined it specifically as this number and how it relates to automobile engines. I'll give you an idea of that with one of my problems in just a few minutes. Okay, now this is the instantaneous quantity, work over time, or excuse me, the average quantity, work over time, but we can describe it in terms of an instant in time, instantaneous power, which is just called P, and it's basically infinitesimal amount of work done in an infinitesimal amount of time. So it's once again just work over time, but we're talking about infinitesimal amounts. Now the numerator of this expression is basically our dot product, force times distance. It's just that the displacement is infinitesimally small, and then we divide it by time dt. Notice that what I end up with here is the derivative of position with respect to time, which is instantaneous velocity. So instantaneous power is basically a dot product between the force vector and the velocity vector. You can think of it as force times speed. Okay, now we're going to keep this topic pretty simple and straightforward. Just take a look at a couple of basic problems to get the idea and why the definition of power is so important from an engineering standpoint. So let's take a look at the first of our two examples. It's the following. And now the situation that's being described here is very simple. We have a machine that's taking a 1 kilogram object such as this, and it's exerting a force horizontally of 10 newtons upon the object. It basically looks something like that. 10 newtons is just a couple of pounds of force. There's a little bit of kinetic friction in on the surface below. Okay, now we don't just pull on the object, however, for a split second or so across the desk. Instead, we do this for 5 full minutes. Now in parts A and B of the problem, we're going to kind of do some chapter 5 stuff first. We'll do a little bit of F equals ma to find the acceleration, and then a little bit of basic kinematics to figure out those two quantities. And as we'll see, the numbers are going to look a little strange. And then why that's important, we'll get to eventually with the power calculations in parts C and D. Okay, now the situation is being described here, very simple. We have our surface like so and our object of mass m equal to 1 kilogram, and it begins at rest, v1 0. And then our machine, it exerts a force like so, F pull, we'll call it to the right hand side, just equal to 10 newtons. Pull in the object, problem will end when the object is over here somewhere, and we'll have some speed v. We'll undergo a displacement here, delta r. And as I said, there's a little bit of kinetic friction here associated with the surface. Okay, the first thing that we do here is just a little bit of F equals ma to find the acceleration. Simple situation. Object's pulled to the right-hand side like so with F pull. Okay, then vertically we have the normal force and the object's weight just canceling. And then also opposite of the motion is the force of kinetic friction. The acceleration A will be to the right-hand side, as is the displacement delta R. So like we would have done back in chapter 5, add up the forces horizontally. We have F pull in the same direction as A, so it's positive. Force of kinetic friction in the opposite direction. So adding up the forces using F equals MA will then give us the following here in the horizontal direction. So, force of kinetic friction is the coefficient multiplied by the normal force, and the normal force is equal to the object's weight. Like so. And then just divide by the mass on both sides to get the acceleration. So very simple situation as we saw back in chapter 5. So let's see, punching in my numbers here appropriately. Friction divided by the mass of 1 kilogram. It ends up being a little bit less than a G, 9.02 meters per second squared. So that basically looks something like that. And now we do this, as I said, for a full 5 minutes. Now 5 minutes is, let's see, 60 seconds per minute multiplied by 5 is 300 seconds. And therefore now in part A, let's use a little bit of kinematics here to find the final velocity v. So like we would have done back in chapter 2, object starts at rest, and now it's 9.02 meters per second squared times 300 seconds. So when I multiply this 9.02 times 300, you end up with 2,706 meters per second. That's just under 3 kilometers per second. So if I come along and I exert a force of a couple of pounds like so, and I do it continuously for 300 seconds, then the object is going to end up moving at a speed of a little bit less than 3 kilometers per second. So what prevents me from doing this? What prevents a machine, at least from very easily doing this? And that's where the power calculations will come in just a few minutes. And then in part B, let's find the displacement delta R by once again doing a little bit of chapter 2 kinematics. So this is basically our position as a function of time equation. In the first term, V naught is equal to 0, the object starts at rest, and then we just plug in the other values. Well, once again, the t, remember, is big, it's 300 seconds. So let's see, 1/2 times 9.02 times 300 squared, and it comes out to be 405,900 meters. So that's a little bit less than 406 kilometers. So that's a few hundred miles. So if I took that object and pulled on it continuously in this manner for 5 minutes, it's like I'd end up in the Mojave Desert somewhere while the object is moving at the speed of a little bit less than 3 kilometers per second. So once again, why can't I do this very easily? That's where our power comes in. So let's take a look now at C and then eventually part D. You guys get out of here. You guys see them hanging around on the roof, by the way, during lunch and nutrition. Next time you're out there during lunch, just look on the roofs surrounding the school, all over the place. All right, next. Okay, now we're going to calculate the average power output, as we sometimes say, of the machine. Sometimes you'll hear the phrase power delivered. Means the same thing. Now this is equal to the work done by the machine, which is the work done by F pull. That's the force that it exerts divided by the time. The numerator of the expression is just the same thing that it's always been throughout the 2 chapters here thus far. It's the dot product between that force vector, F pull, and the displacement vector. You know, our situation is straightforward. The numerator is basically just going to be force times distance, because F pull and the displacement delta R have a 0-degree angle between them. So this is just F pull times delta R, and then divided by T. As we'll see, in terms of watts, this is actually going to be a fairly big number. So in the numerator of the expression, 10 times 405, 900, divided by 300, and that works out to be about 13,530 watts. So what this number now means is that as an average over this broad time interval, what the engine has to do is it has to transfer 13,530 joules of energy directly to the object per second. Now, from an engineering standpoint, this is difficult to do because you're basically constrained from doing so by 2 things. The first thing is, of course, the fuel itself. Presumably, there's some sort of fuel here that has chemical potential energy associated with it, and you then have to convert that into the kinetic energy of the object as quickly as you can. You can only do this so quickly. Like, for example, in the case of an internal combustion engine, basically what happens is that there's a spark from the spark plugs, which then causes the gasoline to explode in the engine block itself. The exploding gasoline then pushes on the pistons, which ultimately then results in the wheels of the car itself turning. So you have to convert basically the chemical potential energy of the gasoline into the kinetic energy of the moving vehicle. You can only do this so quickly because, number one, you're constrained by the fuel itself. You only have so much bang for your buck, if you will, so much chemical potential energy per kilogram. And then secondly, you're constrained by the actual structure of the engine itself. In other words, how quickly can you actually transfer the energy to then the kinetic energy of the object itself? From an engineering standpoint, this is difficult to do. So when you're talking about, say, automobile engineering, you're basically working with the constraints associated with this number. Okay, then the problem kind of gets even worse. There's another problem, if you will. This has to do with friction. So now we're going to calculate what is sometimes referred to as P loss. This is the average amount of energy that we lose as heat per second due to friction. So this is going to be the work done by friction divided by time. So in the numerator of the expression is once again just our work calculation. So it's our familiar dot product like so. And then as we've seen in these horizontal problems, as is always the case, there's a 180-degree angle between the two vectors. Force of the kinetic friction itself is the coefficient times the normal force, when the normal force is equal to the object's weight. So the work here in the numerator of the expression for a horizontal situation is the same little formula as we've seen. And then I just punch in my numbers. Now I'm keeping the coefficient here quite small, but even still, the overall number that I'm going to get here is pretty big. So multiplying out the stuff appropriately, divided by 300 seconds, and this comes out to be about negative 1326 watts. So what this number means is that, yes, as an average over a broad time interval, this is the amount of energy that we're converting into heat per second, 1,326 joules of energy per second. You have to get rid of that heat, because if you don't get rid of that heat, then either A, the object itself can melt, or B, the engine that you're using to do all of this can melt. And obviously you don't want that to happen. Now in the case of an automobile engine, you basically bring this number as low as you can possibly do by making this number here as low as you can possibly do. The way that you do that, of course, is by regularly oiling your engine. So if you change the oil on your engine, you're specifically trying to make that number as small as possible. If you don't oil the engine, this number gets bigger and bigger over time. This then results in the failure of various parts of the engine itself. And then right next to the engine is another device that you may have noticed that is designed to specifically get rid of all the energy as heat. What am I referring to? The radiator. The radiator is basically a big metal drill where you have a fluid that is circulating through it. That fluid, when it passes through the engine block, it's hot. Then when it passes through the radiator, it basically transfers that heat to the radiator itself, which has a big surface area, to get rid of all of the energy as heat as quickly as possible. How many of you have ever been in a car where the radiator has failed? What happens to the temperature in the engine immediately? You'll see your temperature gauge go up like that. As soon as that happens, stop the car and turn it off. The reason why is because if you continue driving the car without dumping all that heat, then basically the engine is going to melt in some manner. Probably the most catastrophic thing that can happen to an engine that fails in this case is what's sometimes referred to as throwing a rod. That basically means that one of the pistons has melted. If that happens, boom, get a new car. Because you basically need to have a rebuilt engine at that point. Yeah.
I was driving on the Grapevine and I was in the left lane.
Were you going up the hill like going north?
And you know how a lot of cars overheat, but there was actually
Sure.
a problem with our car.
Mhm.
And I was in the left lane and I had to get over, but
Sure.
when I pressed on the gas, like not the
Yeah.
RPM would go way up, but I couldn't get any acceleration.
Yeah.
And I had to get over from the left lane going like 10 miles per hour.
Well, was the car overheating or you just had some other failure?
Well, it was overheating, but then we found out that our radiator was...
Okay, yeah, it was the radiator was starting to degrade. You have to change the radiator every so often,
So, yeah,
every
we
X
have to
amount of
change.
tens of thousands of miles. Eventually, the parts will wear out, that's unavoidable. But if you regularly maintain your car, you can stretch out its lifetime. I've got like 15 plus years on my car right now, 250,000 miles. It's still going strong.
250.
250,000.
Wow.
Still going strong.
That's insane. Where'd you go?
Huh?
Where'd you
I went
go?
around the world as many times as I can. Okay, now, the problem kind of gets worse the faster you go. Let's take a look at the instantaneous calculations at the end of the problem. We'll do so when the speed is specifically 2706 meters per second. Mhm.
No question.
Hmm?
So, like you were saying, in a regular traditional gasoline-powered car, there's the combustion delay between the transfer of potential kinetic
Yeah,
energy.
there's a delay in terms of the amount of time that all of this takes. Sure.
But in an electric car, is there any transfer between potential to kinetic, or is it all?
Yeah, in this case, it's electric potential energy in a battery.
Okay. So how?
But you
come-
still have to transfer that. It does so through an electrical current.
Okay. So how come it's so much faster?
Why is the pickup, if you will, so much quicker?
Like the-
Probably because there's less steps in the actual energy transfer itself. In the case of an internal combustion engine, you have to, first of all, get the gasoline into the engine itself. Then you explode it by means of the spark plug,
Right.
which then pushes the pistons, which then turns the axle, which then turns the wheels, and so on. So you've got these multiple steps. Basically, the number of steps are cut down a little bit when you have an electric-powered vehicle or with a hybrid.
So with the battery, there is still potential energy.
Oh, yeah, it's
Okay.
electric potential energy, absolutely. Okay, now, here at the very end of the problem, as I said, the problem kind of compounds itself in the following way, as you'll see. Let's say that we're talking about the moment here where we're traveling, where the object is moving, that is, at 2,706 meters per second. So the instantaneous power output of the machine will now be the dot product between F pole and the velocity vector v. Okay, this is basically force times speed here because these two vectors are in the same direction for our problem here. So it's just F pole times v, but it's a big number. We're only talking about a 1 kilogram object here, remember. It's 10 newtons multiplied by 2706 meters per second. That's 27,060 watts. So what that means is that if I wanted to keep this object moving at 2706 meters per second, then the machine would have to supply 27,060 joules of energy to the object per second. Once again, you run up against a problem here in terms of the constraints of the machine itself as to whether or not it can transfer that energy that quickly. And then with friction, the problem kind of gets worse and worse too as time goes on. So now we calculate the instantaneous power loss. So that's the dot product between the frictional force vector and the velocity vector. Okay, these two guys in our problem is they're just in the opposite direction. Cosine of 180 is equal to -1. So, and then the force of kinetic friction is the coefficient times the normal force, which is the object's weight. So you have this little formula here for the instantaneous power loss, which is all heat as it is due to friction. Okay, this is also a big number, even though the coefficient is small. And this comes out to be negative 2652 watts. So at this moment, you basically have to get rid of that amount of energy as heat per second, otherwise things are going to begin to melt on you. So when we design machines to do some form of work, essentially we have two problems that we wrestle with. Number one, how quickly can we transfer the energy from, say, chemical potential energy into the kinetic energy of the object? And then secondly, how quickly can we get rid of the heat that is generated in the process, right?
On the instantaneous power is exactly double the average.
It's just how the numbers worked out here.
So it's
That's
not.
all. Yeah, don't try and like read anything into the actual numbers themselves.
Darn it.
I'm just going directly from the definitions, easy enough to calculate. Okay, then lastly, let me give you a basic understanding as to what is meant by a horsepower.
A horse.
Here's a problem involving a horse. regards, by the way, to an automobile, just with a normal internal combustion engine, does anybody know approximately how efficient they are? That is, like what percentage of the chemical potential energy of your gasoline actually ends up being the kinetic energy of the car itself?
23%.
5%
It's like 5%, yeah.
Wow.
Yeah, most of it is burned off as various forms of heat due to friction and energy transfers that take place, et cetera.
Is that what determines your NPV?
In part, yeah. With regards to the internal combustion engine, it's, it's technology now, it's over 100 years old. It's about as good as we can make it. We can do various tricks to tweak it and try to make it more efficient and so on and so forth, but we're eventually gonna have to go to a process, of course, where we're using less and less actual fuel, using less and less gasoline, because it's all gonna run out eventually. So then therefore, the future is probably that everything at least will be a hybrid vehicle, probably within the next decade or two.
And flying.
Yeah, and flying machines, and everybody driving around with drones.
Yes.
Exactly.
Why can't you make it more efficient?
Basically, the technology is mature. You can only get so much bang for your buck, if you will, from the fuel that we use and then transfer that into the kinetic energy.
We're gonna be
You
able
can't
to
make it any better, basically, than it is.
transform.
What if there's some new
energy
discovery?
from
Could be,
air.
but frankly, don't hold your breath.
And we just shave our head.
Okay. Okay, now in this particular problem, we're once again keeping it easy. Let's say that we have
Yeah, little
the force that the
buckets on
horse
the
is
seats.
exerting, we'll call it F pole, equals
Professional
40
driver.
pounds.
Because I'll have the.
And we'll just have it in the same direction as the velocity vector v of 10 miles per hour. Now, it does say in the problem that the horse is pulling at a constant speed. This means that the instantaneous power output of the horse and the average, they're actually the same numbers. Okay, now before we actually do our dot product here, which will just be force times speed, we do have to be in the correct units. Miles per hour has to be in the base units for speed in the English system, which is feet per second, so we do have to convert. So I'm going to multiply by 1 hour per 3,600 seconds, like so. And then there's 5,280 feet in a mile, so multiply by 5,280 feet per mile. And then I'll be in the correct units. So 10 miles per hour, by the way, is kind of like a trot for a horse. That's a brisk jog for a person. So 10 over 3,600, and then times by 5,280. And that comes out to be about 14.67 or so feet per second. So that's the number that we need now in the correct units to get the power output of the horse. So P horse, okay, as I said, it's just force times speed because these two vectors are in the same direction. F pole times V. And this then works out to be the following. I'll have, first of all, 40 pounds, and then multiply by 14.67 feet per second. This then gives us our answer in terms of foot-pounds per second. It's about 587 per second. Now, those are the basic units of power in the English system, but we then define it in terms of a horsepower by doing the following conversion. I'm going to take this quantity here, multiply it by its conversion factor. You don't need to know this off the top of your head or anything like that. But 1 horsepower is 550 foot-pounds per second. Cancel, and it's a little bit more than 1 horsepower, as you can see, not by much. So 1 divided by 550 is about 1.07 horsepower. So you have a horse basically trotting along, pulling a light load here of, say, 40 pounds. The amount of energy per second that is necessary to do this is basically 1 horse, 1 horsepower. Yes?
Why is torque also referred to as foot-pounds?
Torque actually has the same units, force times distance, if you will, of work and energy. But torque is the rotational analog of a force. Even though they have the same units, they're not quite the exact same quantity. We save, however, torque and its cousin, angular momentum, as an AP topic, however. Okay, now with regards to horsepower here, you can see that this is 1 horsepower. Those of you that are like into cars, does anybody know what the power output of high-end automobile engines happens to be? Nick?
1,000.
Yeah, over 1,000 horsepower, something like that, for the best sports cars, that sort of thing. So it's like, 1,000 of this. That's basically what the internal combustion engine would do. That's obviously a lot compared to just a single horse. Okay? Yes?
How come a horse can output more than a single horsepower?
Well, this is a horse pulling a light load in this case of just 40 pounds, and it's moving along at human jogging speed. Usually in agriculture, they may be pulling larger loads. They could even be running faster depending upon what it is that's being done. But frankly, we don't really use horses in agriculture anymore. It's all done by very high-end machines.
So when they use horsepower, does it
Robo
the power of a car? Is there like an average?
So the term horsepower is an old archaic term, and it didn't really have this strict numerical definition until the Industrial Revolution. But it was just kind of like a rough idea, if you will, of how much work a horse could do per time. It could basically do something like this.
Okay, so horsepower wasn't used as a variable for like complicated.
It was just a qualitative description for a long period of time. It was then quantified in the Industrial Revolution, given an actual numerical value.
Okay.
So, okay? We don't need to beat a horse to death. Henry?
So before the Industrial Revolution, and before that whole conversion thing, were they like, you know?
Well, remember that the basic physics of work and energy started to come into maturity in the early 19th century, which is when the Industrial Revolution began. So that's when around the time we started building machines that could do work over time. That's when power became an important calculation.
But if something needed like 2 horsepower, would you need 2 horses?
Yeah, people would just have a ballpark assumption,
Right.
like, okay, in order to plow this field, I'm gonna need a horse doing this or 2 horses doing that,
Right.
that sort of thing, okay? All right, good.
What about ox?
All right, so let's go ahead now and get to the review.
You know oxen.
Yeah, oxen.
How many oxen do I need? We'll just type in the horsepower.
Cheetah power.
That's just too big a number, you know?
Mountain power?
All right, as is always the case,
You need like 3
you're allowed a 3
trillion.
by 5 note card for the exam. The same rules in the first semester for exams, just roll over here into the second semester as well. There will be a little bit of qualitative extra credit on this exam, but it's basically otherwise 5 problems. It's going to be worth only 25 points. Okay, it's going to cover the following topics. So the first thing that we really did after we got back from winter break was go over spring potential energy, or the basic form of spring potential energy is 1/2 kx squared. And then we immediately started to apply it to situations involving conservation energy, not just with spring potential energy, but also with gravitational potential energy as well, like in vertical spring problems and stuff like that. So next we have conservation of energy, where our basic expression is the following. And then remember that everything kind of came together, that is for chapters 7 and 8, into our next topic with respect to non-conservative forces. We basically combine everything into one expression. So our one expression, remember, was as follows. Work done by non-conservative forces. And the only non-conservative forces that we looked at was a push of some sort, or the force of kinetic friction or air resistance or something like that. And that then results in the right-hand side of the expression. Now, if there are no non-conservative forces present and the left-hand side is equal to 0, then it's just a conservation of energy situation. And then, last time in class, we had our big topic for that day, which was Newtonian gravitation. Remember that in its Newtonian form, gravitational potential energy is the following function. And then we use this in a number of examples. So. And then lastly here today, our brief look at power. First of all, we have the average, which is just work over time. And then the instantaneous, which is the dot product between the force and the velocity vector. It wouldn't be anything more complicated than the horizontal situations and whatnot that we would not too elaborate. Okay. Next is the review handout itself. Because we do have a slightly shorter time here to review, it's a slightly shorter handout than normal. It's 4 problems.
5 on the
5 on each.
So what one we do that?
Sean, you're always looking for that angle.
I think that's the upper hand.
Yeah,
If we finish rolling, can we play heads up 7-up?
wait, huh?
If we finish rolling, can we play heads up 7-up?
Let's see how far you can.
One out.
All he's talking about. Here in the classroom, we kind of boring game. They'll just be running around in the rooms. All right, now, here's how I've structured the review. What I've done is I've taken our basic examples, variations of them, and I've kind of broken them down into small parts. So taking a look at problem number 1 here first. Problem number 1 is where we begin by initially compressing a spring, release the object from rest. We're ultimately going to find the speed of the mass as it passes through the equilibrium position, and there's a little bit of friction. Part A, however, I just have you calculate the work done by friction. Part B, I just have you calculate the change in the spring potential energy. Part C, then you start to put everything together. So it's like I'm taking our normal examples and just breaking them down into small chunks here as we work through the examples. So go ahead and double up, triple up, etc. appropriately. Go ahead and get started, and in a little while I'll start laying out number 1 of the work.
All right, children.
Dexter? All right, so yeah, go ahead, double up and triple up, and begin.